Hi everyone. So in this section what we're interested in is covering a couple of portions of the book that pertain to equations for lines and different ways to manipulate equations for lines, different forms, so point slope form, slope-intercept form, standard form, and then thinking about how to find lines that are perpendicular, lines that are parallel to whatever is the initial line, and then thinking about ways to solve systems of equations through substitution and elimination. All right, so first off, in section 2.4, we remember when we see y equals mx plus b, or y equals b plus mx, we know what we have is a linear relationship. We have a linear function. So y here is a linear function of x. Y is increasing in x for positive m and decreasing in x for negative m. It's according to the slope, right? The slope is the rate of change. We can also think of this as a linear equation in two variables living in the xy plane, right? We have the x-axis, we have the y-axis. This creates a plane, creates like a big infinite rectangle, and the lines that we're studying live in that space. So that's what we're thinking about here. Okay, so the first thing we'll do is we'll think about the line in standard form. So ax plus by equals c is standard form of a line where we have a, b, and c being constants. And take a look at this for a second. So this is standard form of the line. This is different than y equals mx plus b. Right? You might be tempted to think that c here is the intercept, but it's not the intercept. It's only part of it. In order to get the intercept, right, we have to divide through everything by b. So c over b would be the intercept. And if we wanted to get this into y equals mx plus b form, or y equals b plus mx form, we'd subtract ax from both sides and we'd divide through by b. So the slope would be minus a over b, and the intercept would be c over b. Okay. So let's work with this line. So consider the equation 3x plus 4y is equal to 24. Let's find the x and y intercepts. Let's show the graph as a line by putting it into slope-intercept form. Then give me the slope. And then let's find the point on the line where the x-coordinate is 12. And use that point to write the equation in point-slope form. So stop the video, go ahead and do this. All right, now resuming. Well, in order to find the x-intercept, what do? We set y equal to 0, and then we solve for x. In order to find the y-intercept, what do? We set x equal to 0 and solve for y. And what this is giving us is the other coordinate when we fix one portion of the ordered pair. What does that mean? Well, remember the x-intercept it's an ordered pair, right? So we have some x-coordinate for finding and some y-coordinate. Well, it's not just any y-coordinate, it's a y-coordinate of 0 because that's what's necessary to be on the horizontal axis. So think about our ordered pair. We are fixing the y value at 0, and then given this equation, we're finding what x must be to make that true. So that's what we've done here. So what's our ordered pair? Corresponding to the x-intercept, it's going to be the ordered pair 8, 0. We do the same thing with the y-intercept. We know the y-intercept has to have an ordered pair where the x-coordinate is 0. So we have a 0 and then something, and we're going to find that something. So we set x equal to 0. We solve and we find, oh, when x is 0, y has to be 6. So this gives us the ordered pair 0, 6, and that is the y-intercept. Now if you want to graph this line, a really low-cost way to do it is to just plot those 2 points, 8, 0, and then 0, 6, and connect the dots. Okay, so another thing we can do is we can put this thing into slope-intercept form and then find the slope of the line. This amounts to nothing other than just solving for y. So we know how to do that. Let's just solve this thing for y. Here we have it, y equals 6 minus 3/4 x. The slope is minus 3/4. This should be no surprise. Our y-intercept is 6, right? We found the y-intercept is 6, and the b portion of our slope-intercept form gives us the y-intercept. So that's a good check on our earlier work. Okay, so the last thing we wanted to do is, whereas previously we fixed a value of x at 0 and found the corresponding y value, and that was our x-intercept. And then previously we fixed the value of y at 0, or fixed the value of x at 0, and then found the value of y, and that was our y-intercept. Well, now we're going to fix the value of x at 12. And we're going to find whatever must be the corresponding y point. So let's plug in 12 for x and evaluate, and then solve for y. We find, oh, when x is 12, y has to be minus 3. If it's going to be satisfying this equation, meaning if it's going to be on the line. And if you'd previously plotted those points, you can now go and draw in the point, the ordered pair 12 minus 3, and you'll see it lies on your line, unless you've done something wrong with your tick marks on your graph, in which case then you just need a better graph. Okay, so the last thing is we can use this point and its slope to be able to build point-slope form. So point-slope form is just our y minus our y variable minus some y value is equal to the slope times the quantity x minus the x variable, or value. Well, our value, our ordered pair was 12 minus 3, so our x is 12, our y is minus 3, our slope is minus 4. So I'll just enter these things in, and here is my slope, or here is my point-slope form. It is y plus 3 equals minus 3/4 x minus 12. Right, we have our point. Here's the x-coordinate, here's the y-coordinate, here's our slope. We have a slope, point-slope form. So that's not always pretty to look at, and maybe we're interested in looking to see if this actually matches what we had earlier. So let's do that. Let's just distribute this minus 3/4, and let's move this 3 to the other side and see if we get in y equals mx plus b or y equals b plus mx form, or our slope-intercept form, we get the same value we had before. And sure enough, if you perform those algebraic operations, you'll end up with y equals minus 3/4 x plus 3. Or plus 6, sorry. And what this tells us is that this representation in point-slope form is mathematically equivalent to this representation, because we got from here to here just by following the rules of arithmetic. Okay, so the next thing to think about is the equations of horizontal and vertical lines. So moving from left to right, a line with positive slope rises, a line with negative slope falls. What if the slope is 0? Well, if the slope is 0, it neither rises nor falls. It's just a horizontal line, right? If the slope is 0, its rise is 0 over whatever for run. When the slope is undefined, then the line is vertical. So if our run is 0, but our rise is potentially infinite, then we have a vertical line and slope is undefined. So therefore, we can solve the following. Is x equal 5 horizontal or vertical? Is y equals minus 2 horizontal or vertical? And then give the equation for the horizontal axis and the vertical axis. All right, so pause, stop, think about it for a second. Probably the easiest way to solve this, now returning, is draw your tick marks, find where x is equal to 5, and then just draw a straight line. Why straight line or vertical line? Well, because we've fixed this particular coordinate for our ordered pair for x at 5, and all points that satisfy that line must have 5 for their x-coordinate. What about y? Well, now we want a horizontal line at minus 2. Why? Because all points lying on the line has to have minus 2 for its y-coordinate. So we're thinking of ordered pair something comma minus 2. And what about the horizontal axis and the vertical axis? Well, this requires a little pause. You want to think a little bit. Okay, if we want the equation of the horizontal axis, right, this is a line, it's a horizontal line. We know 0 is involved. How is 0 involved? Well, if we are on the horizontal axis, think about all these things. This is collecting our universe of x-intercepts, and every x-intercept has some value for x and then a 0 for y. So this is the line y equals 0. The horizontal axis is the line y equals 0. And similar logic for the vertical axis tells us, oh, this is categorizing or collecting all of our y-intercepts, all of which have 0 for the x-coordinate and then some y for the y-coordinate. So this is the line x equals 0. Okay, so just going over this work, was x horizontal or vertical? Well, it's vertical. Quite literally means all points on the line have an x-coordinate of 5. Because it's a vertical line, we cannot put this in point slope form because it doesn't have a slope. What about this one? Y equals 2 minus 2. Well, this means all points on the line have a y coordinate of minus 2 for all values. So rise over run, well, rise is equal to 0, like I said, so the slope is 0. It's just a horizontal line. Okay, and then here's the answer. I have not duplicated the logic that I told you a second ago. The horizontal axis is represented by y equals 0. Why? Well, the horizontal axis is collecting all of our x-intercepts, all of which have some x-coordinate, and then a y-coordinate equal to 0. The vertical axis collects all of our y-intercepts, all of which have an x-value, x-coordinate of 0, and then take on whatever y-coordinate they need to be a y-intercept for their line, right? Okay. And then more generally, the graph of the equation y equals k is horizontal, its slope is 0. The graph of the equation x equals k is vertical, and its slope is undefined. This is cool. I think it's nice to look at this. Let's understand the pattern and use this to guide your reasoning. I wouldn't recommend memorizing this. I would think probably what you want to do is memorize a process that will help you uncover which is the right representation of horizontal and vertical lines, right? Think about what the interpretation is. Think about how you can draw a picture or whatever. And that's going to be more valuable than memorizing this relationship. Okay. What about perpendicular and parallel lines? Well, parallel lines are two lines with the same slope. Perpendicular lines are two lines with slopes that are negative reciprocals of each other. So if you have slope, you have L1 and L2 are two lines, slope M1 and M2. Lines are parallel if M1 equals M2. If the slope of the first line is equal to the slope of the second line, their y-intercepts are going to be different, otherwise it's the same line. And then the lines are perpendicular if M1 is equal to the negative reciprocal of M2. All right, so if the slope is 3, then the slope of the perpendicular, slope of any line perpendicular to a line with a slope of 3 is a slope of minus 1/3. And of course, there's infinitely many lines that are perpendicular to any given line. Think about what's going on. Think about a line going through space which stretches to infinity in both directions. You can cross that line in an infinite number of places because there's an infinite number of points along that line. And all those lines are going to have, if they're perpendicular, we're going to have the slope equal to the negative reciprocal of the original slope. Okay, so that realization is important when we do some examples. Find the equation for a line parallel to the graph of y equals 12 minus 3x with a y-intercept of 7. Find the line parallel to the graph of 5x plus 3y equals minus 6 containing the point 9, 4. And then the line perpendicular to the graph of y equals 5x minus 20 that intersects the graph at x equals 6. Okay, well, let's pause the video. Now returning, let's think through these. Well, the line parallel to the graph of y equals 12 minus 3x with a y-intercept of 7. It's parallel, right? So it's got to have the same slope of minus 3. So we know we're going to have y equals minus 3x plus something. Oh, well, it's got to be this y-intercept plus 7. The line parallel to this graph, we have to change this into, this is in standard form right now, right? This is our A, this is our B, this is our C. We have to change this into slope-intercept form. That will give us that will give me my slope. Then I build a new line using the negative reciprocal of that slope and this point. So then I use point-slope form. And I do something, oops, sorry, I was reading ahead. Parallel, we're going to use the same slope. When we do this, we'll get this into y equals mx plus b. We'll use the exact same slope when we're going to point slope form because we're getting a parallel line. It's down here that we're trying to get the perpendicular line. So now we're going to build a line with a slope of minus 1/5, and then we're actually going to have to be clever. We're going to have to figure out, we only have the x coordinate of the point. We got the intersection of the point where they intersect. We want the graphs, this line and the one that's perpendicular to it, to intersect specifically at x equals 6. So let's find the y value, and then we can find the equation. Okay, so first off, this one was straightforward. Line parallel to the graph of y equals 12 minus 3x with a y-intercept of 7. The lines are parallel, so the slopes are the same. So it's minus 3. We were given the new y-intercept. It could have been anything. We're told it's 7. Cool. So this is a line parallel to this line with the y-intercept of 7. Okay, now we want a line parallel to the graph of 5x plus 3y equals minus 6 containing the point 9, 4. Cool. So we put this thing into slope-intercept form. If you do this, you find the slope is m is equal to minus 5/3. All right, we're moving our 5x to the other side, divide through by 3, minus 5/3. So the parallel slope has the same slope, but it's parallel. So we want minus 5/3 as our slope, and then we, using slope-intercept form, to give us the equation of a line going through the point 9,4 with a slope of minus 5/3, well, we just evaluate. Simplify down, we'll find y is equal to 19 minus 5/3 x is a line that's parallel to this one, but it goes through the point 9,4. And then lastly, we have perpendicular lines. So if the original slope is 5, we know the slope of the line we're building has a slope of minus 1/5. Why? Because they have to be negative reciprocals. If this would have been 6, then our slope that we're trying to find for our perpendicular line would have been minus 1/6. Okay, but it's not. Our slope is 5, and so our perpendicular line has slope minus 1/5. The lines intersect at the point, or at a point with x coordinate equal to 6. Well, let's find the corresponding y. So we'll evaluate this by plugging in 6 here. So we have 30 minus 12 is, or minus 20 is 10. So the point is 6, 10. Now we can use point slope form. Here's my point, or here's my slope, here's my point, and we find y is equal to 11.2 minus 1/5 x, or 0.2x, same thing. Okay, so the next thing we're going to do is 2.5, we're going to think about recognizing whether or not a particular situation can be modeled with a linear expression. So one way we do this is we'll look at a series of tables and we'll see if the table could be represented by a linear relationship. To do this, we'll see if the rate of change between any 2 points is constant. So here's the first one. Is the rate of change between any 2 points constant? Well, we'll see our x is increasing by 2's, our y is increasing by 3's at all points. So sure enough, this can be modeled by a linear function. Each time x increases by 2, we have a 3-unit, I put 4, we have a 3-unit increase in f of x. We see this, right? 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10, plus 3, this should be 3-unit. We have a 3-unit increase in f of x. This means the rate of change between 2 consecutive points is 3/2, right? So 1.5 rather than 2. That's irrelevant for our conclusion. Our conclusion is that this function is linear over the points and might be linear in general. I say might because we don't know what's happening between these points. Maybe there's some squiggly line segment in between, right? Maybe this whole thing is a bunch of squiggles and I've just given you points that happen to line up on a line. You never know. Okay. So determining whether a set can be modeled by a linear function gets harder when the x's don't increase by the same amount. So between here, we have a jump of 2, here's a jump of 1, here's a jump of 3. And what's happening to that? To the y values? Well, we can check for linearity by computing the slopes between consecutive values. So 5 minus 11, 1 minus 1. And we'll check at all these points, and all these are minus 3. So the average rate of change between consecutive data points is a constant. The function might be linear. Why are we doing this? Well, we're doing this because we have a non-constant increase in our x, right? We're not always increasing x by the same amount. In the previous table, x went up by the same amount. It went up by 2 units. Well, here we have x going up by 2, then going up by 1, then going up by 3. And so we have to account for this by just computing the slope between these 2 points, right? This is the x value, this is like the y value, x value, y value. So we have ordered pairs. We use our slope formula. We calculate the slope, and then we interpret it. Okay, so let's look at this last one. If your eye is really clever, you've seen what's happened. I changed this from minus 7 to 10, to minus 10. Right, so we know, if you just caught that, we see that this thing can't be modeled with a linear function. What's going on? Well, by virtue of having changed this changes our slope calculation between this point and this point. The line got steeper, right? It got steeper, pointing down faster. So the average rate of change between consecutive data points are not all equal. So this is not a linear function. Okay. And the last thing is solving systems of linear equations. So for any x and y, any x, we can solve for the y to get the corresponding y value and vice versa. A solution of a system of equations is a set of two or more, or a system of equations is a set of two or more equations, usually two, but in some cases we could have as many equations as we want. It's a very unwieldy system to have to deal with. And then a solution to a system of equations is just a set of values for the variables that makes all the equations true. Okay. So suppose we want to solve by substitution. What do? Solve for one of the variables in one of the equations, substitute into the other equation to get an equation in one variable, solve the new equation, then find the value of the other variable by substituting back into one of the original equations. Well, let's see it. So suppose we have 2x plus y equals 11 and 3x plus y equals 14. We can solve for one of the variables in one of the equations. The obvious way is just pick the first one, solve it for y, then substitute in where y appeared in the second equation. I'm now going to put the quantity 11 minus 2x. So notice this one right here is 3x plus the quantity 11 minus 2x equals 14. That's just this right here, being replaced with this expression once we solve this for y. Okay, you could have actually solved this one for y and then plugged into this equation, or you could have solved either of these for x and then substituted into the other for x, and then you get an equation that's only in terms of y. Now, that'd be mathematically correct. It would also be highly inefficient, but you could do it. All right, so going back to the work, I solved this for y, I substituted into the other equation, I got an equation in a single variable, and I solve for x. X is 3, so y is equal to 5, right? 11 minus 6 is 5. Okay, now what about solving by elimination? Well, we want to get standard form. If they're not already in standard form, then we multiply one or both equations by a constant with the goal of making the coefficient of the first one, the coefficient of x, for instance, or y, for instance, in the first equation equal to the negative of the coefficient of the x variable, for instance, or the y variable, for instance, in the second equation. Then we add them up, and we have a single equation with a single variable. And then solve the remaining equation for the remaining variable, then plug back into one of the equations. Basically what you're going to do is you're going to stare at your system of equations and say, when I add one to the other, do I need to do anything, or what can I do so that when I do this addition, one of the variables evaporates, cancels out? Sometimes it'll be obvious. Like in this example, it's very clear that we can get rid of the y's. Other cases, we'd have to get rid of the x's. In other cases, we have to work a little bit harder to figure out what to multiply to make something like that happen. Here it's pretty obvious. If I'm going to add this equation to this equation, I just need to multiply one of these by -1 so that my y's drop out. So I'm going to multiply the bottom equation, the second equation, by -1. So I'll get -3, I'll get -y, and I'll get -14. That's exactly what I get here. I've got these big parentheses indicating that I can't just multiply this by -1. I have to multiply everything else to retain the equality statement. Well, anyway, once I do this, now I can add up 2x plus -3x, y plus -y, 11 equals 11 plus -14. So here's that work. This looks kind of scary. Where on earth did this come from? Well, this is nothing other than indicating that we're adding this to this. It's just grouping. And we're adding this to this, and we're adding this to this. And when I write this here, clearly adding vertically like this is identical to adding horizontally like this. I wouldn't even need these parentheses. I just put them in there because I think it makes it a little bit easier to see exactly how this addition is progressing by grouping. Although the grouping and regrouping is just for convenience. When you do this, we get a -x, we get a 0, and we get a -3, so we have -x is equal to -3, or x is equal to 3. Then plugging back into the other equation, we find y is equal to 5. Surprise, surprise. It's the same equations which we had previously solved, so it better check out like this. And my last comment is that it's probably a good exercise when you have an equation, system of equations from the problem set that tells you to solve by elimination. We'll do it by elimination, then try by substitution. And when you have one that says to solve by elimination, or by substitution, do it by substitution, then check by elimination. The reason why is because that'll give you practice working with the procedures, and you'll know if you're right or wrong by virtue of having previously solved the problem. So anyhow, let me know if you have questions.